Hello and welcome to this video on building linear models from data. And this is the third part, the third video on this objective, building linear models from data, titled Fitting a Line to Data. Now I want to preface this video by saying this material is more intended for the beginning/intermediate algebra student. So I'm not going to be fitting the best line to data, the best fit line or the regression line for those of you who are coming from a statistics class watching this video. That is not the intention of this particular video. So if you're looking for finding the best fit line or regression line to a set of data, search for that elsewhere. Alright. So let's begin. I have an example that came up a couple videos ago in the first video of this 3-video series on building linear models from data. That was the video on scatter diagrams or scatter plots. And it was where I was given this table. All right, the data listed below represent the total cholesterol in milligrams per deciliter and age of males in years, right? So each row represents one person, one male. So there's a 25-year-old male in this sample that had a total cholesterol of 100 milligrams per deciliter, and so on, right? Down to there was a 65-year-old male in this sample whose total cholesterol was 269 milligrams per deciliter. And in the first video in this 3-video series on building linear models from data, we were asked to make a scatter diagram of this, which I did in that video, and here was the resulting scatter diagram. Alright, so all of these ordered pairs, 25 to 180, 25 to 195, 28 to 186, etc., are plotted here. Now some point is, the marker I was using bled a little bit on some points, but there are 10 ordered pairs in this graph, right, of these 10 relationships between age and total cholesterol of certain males. And here's the scatter diagram: total cholesterol of males at a certain age. My horizontal axis represents the number of years, the age. My vertical axis represents the number of milligrams per deciliter, that's the total cholesterol, and each of these points again corresponds to one of these pairs of numbers. My horizontal axis, every square represented 5 years. My vertical axis, every square represented 20 milligrams per deciliter. Alright, so now that again, you can go back to that video if you wish, see how this was made, how these points were plotted, these 10 ordered pairs here. Shouldn't be too difficult. And then we're going to be asked to do some other stuff with this now. The title of this video is, Fitting a Line to Data. If you notice here, these 10 points in my scatter diagram seem to be trending upward to the right. They start off low down here, and then as I move up in years, as I move to the right, the total cholesterol seems to be increasing. Now they're not all on a straight line for sure, right? They're not all on a perfectly straight line, but they do seem to be tending upward, so in the direction of a line with a positive slope. So I would say that these the variables here, age and total cholesterol, have a positive linear relationship. If you want to talk about the relationships, see a video on the relationships between variables. That was in the second video in this series of 3 videos on building linear models from data. Alright, so part A. First thing I'm asked to do here, I'm going to be selecting 2 points. Let me move the scatter plot up so we can see it. So there's a scatter plot for that table. And what I'm going to be doing in part A is select 2 points and find a linear model, right, or write a linear equation that describes the relation between the 2 points. So a linear model or a linear function. You know, typically I'll put it in what's called slope-intercept form, right? Our basic linear model looks like this. Now my variables here were called x and y, right? X for age, that was the independent variable represented by the horizontal axis. Y for total cholesterol, the dependent variable represented by the vertical axis. All right, and that was y equals, you know, m times x plus b, right? And I put up videos prior to this on, you know, basic linear functions. Or you could say y of x, right? You could also write this in function notation. The value of y at x equals, you know, some m times x plus some b, where these letters meant something, right? The letter m represented the slope of the line, and the letter b represented the y coordinate of the y-intercept. Right, if I were to graph a line, right? Y-intercept, remember, is a point of the graph on the y-axis that would have an x-coordinate of 0, and if x were 0, right, you know, anything times 0 is 0, and then you have plus b, you'd have b as the output, right? 0 comma b. All right. So I'm going to try to fill this in. I'm going to try to pick 2 points here that I feel represents this data the best, that seems to follow in the pattern, right? Because again, I'll use a little ruler here. Here's the scatter plot. You know, if I use these 2 points down here, say this point and this point, you know, if I drew that line, that line's kind of below all the other points. Doesn't seem like all the points follow in that direction of a line like that. Maybe if I use these 2 points, maybe a little better. I'm going to try to get it as centralized as possible. So I'm thinking I'm going to use like these 2 points here. This point in the middle of that cluster of 5, right, very centralized, and then this point at the end here. And it looks to me like those would be 2 good points, so that a line going through them would be a good line that shows the pattern that the points are trending in. So the 2 points I'm going to select. And again, you don't have to select these 2. The 2 points I'm going to select are this point here, which has an x-coordinate just below, you know, 25, or I'm sorry, just below 30, and a y-coordinate above 180. So let's see, what point was that? So that's this 28, 186 point. All right, 28, 186 is this point right here in the middle of this cluster of 5. So 28 for the x, the age, 186 for the y, the total cholesterol. So that's that point in the middle of cluster 5. And again, I think this one over here would be a nice line, would create a nice line that shows the pattern pretty well, the pattern that these seem to be trending along. So 28, 186, and then this point out here is the one where the age is 65 and the cholesterol is, you know, maybe there's that 269. It's between 260 and 280. So it's this point right here. So 65, 269. 65 for the age, 269 for the cholesterol. All right. So I'll cover the scatter plot for now, and we'll talk about writing the equation of this line I'm looking for that goes through these 2 points. All right, so in order to write the equation of a line, you need 2 points, right? And think about what these are, right? I want to try to fill this in. First, I'll need the slope. All right, we have 2 points. You can calculate the slope. All right, so remember how slope is calculated. If you've seen other videos on the calculation of slope, remember the slope is a rate of change. It's the change vertically, the change in the y coordinate divided by and then the change in the x coordinate, right? And I've talked about these symbols in previous videos where this means change in. This is the Greek letter delta, these little triangles. Delta y over delta x, change in y over change in x. All right. And the way you calculate that is like, so imagine I'm starting here at this point, right? And that was this point in the middle of the 5 right here. And I travel to this other point on the line that I'm going to draw, and I'll draw it in a second with a ruler. But so I'm going from this point to this point. You know, how much did the y coordinate change? So let's look at the y coordinates. Went from 186 to 269. So the change in y is 269 minus 186, and that's the numerator of my slope. How much did the y coordinate change, the dependent variable change? And since again it increased, right, went from 186 up to 269, that's a positive change. Anytime there's an increase, you should have a positive number for your change, which I will have here, a large minus small. That'll be positive. And then for the change in the x, the horizontal change, again, I'm going from this point to this point, 28 to 65. You always take last minus first. I do second minus first for the y. I have to do the second value minus the first value for the x. Do those in the same order. So 65 minus 28. And again, another thing I could say too is that the x coordinate increased, right? It went from 28 and increased to 65. And when there's an increase, that is a positive change. So you see how 65 minus 28 will leave me with a positive number. Okay. Great. And then let's simplify this. All right. And if there's a decrease, that's a negative change, right? If you ever have a decrease, you should have a negative number to represent that change. Just pointing that out. All right. So the numerator, we have 269 minus 186. Right. So the numerator that's a difference of 83. All right, and that's how much the y coordinate increased by 83. And then the denominator, 65 minus 28 is 37. All right, 65 minus 28, 37. All right. So there was an increase in the x coordinate of 37 units. Great. And I believe this is as simple as it gets, and I'm going to punch this in my calculator here, and we'll do 83 divided by 37. Yeah, it's some pretty crazy decimal. So this is approximately, this little symbol here, remember, it's not equals, it's approximately, it's about 2 point, and I'm saying 243 repeated, right? 243 and then 243, 243. So about 2.243. I'm going to keep this though, right? I am going to keep this as the slope for now, right? Just to make sure things stay exact and I don't round things until the very end, right? Because the more you round numbers throughout a problem, if you round in this step and then round in the next step and then round and round and round, the more you keep rounding throughout a problem, the less accurate the final answer will be, because you'll have rounded so much. So yes, this is the slope of the line rounded to the nearest thousandth here, 2.243, but I'm going to keep it as this exact fraction, right? 83 over 37. All right. And I should really put some units in here too, because these variables y and x actually have units involved. So really the slope here is 83 37ths, and the numerator, right, that's the change in y. And what did y represent? Cholesterol. And what were the units on that? That was milligrams per deciliter. So the numerator units is milligrams per deciliter, and that's per, right? And the denominator units, x was age, that's per year old. All right, let's say per year. So 83 37ths milligrams per deciliter per year, right, or per year of age. is the slope of this line. All right, I'm going to fill that in. All right, so here's our linear model now. Okay, so now the model looks like this. Y equals the slope of my line, this rise over run, change in y coordinate over change in x coordinate. Well, when I pick these 2 points that I felt was a good line going through these all these points up here, y equals replacing the slope with 83/37 times x, and then we have one more letter to find, one more letter to fill, plus b. So I found the slope. Now I'm going to find this b. Now how do I do that? Well, that's where one of these points comes in. All right, that's why you need the points. You need the points to find the slope and also to find this b, this y coordinate of the y-intercept. All right, so now I'm going to use one of the points to find b. So one of the points that I'm going to be drawing this line through, that I feel shows the pattern of all the scatter diagram, I'll take, it doesn't really matter, either one. Let's take the 28/186, the one with some smaller numbers to work with. All right. So remember, this is our x value, right, the age. This is our y coordinate, the cholesterol. And we're writing an equation that this point is going to be on, right? I'm going to be drawing a line going through those 2 points, right? This one here in the middle of the cluster of 5 and then this one out here. I'm going to be drawing a line going through those 2 points that'll tend to be that the pattern of the points seems to be following. Right? So we're writing an equation for that line, all right, this equation here with this point on it. That means that this point is a solution of our equation. This should satisfy the equation we're trying to write. So when I replace x with 28 and y with 186, this should be a true statement, this model I'm drawing. So I do that. I replace x with 28 and y with 186. So the left side becomes 186 equals, and the right side is 83/37 times, and then replacing x with 28, and then plus b. Okay. Now I have what I'd like here. Now this is like 28/1. Remember, any fraction without a denominator has a denominator of 1. So I can multiply these, multiply fractions. You just multiply the numerators. I'm going to use my calculator, make it a little quicker. So the numerator, so over here I have 186, and here 83 times 28 is 2,324, and the denominator is 37. Okay, and then we have plus b, and you see now once I plug in this point to our model, we can solve for b. Right now I have b by not by itself, but this equation only has the variable b in it. So now I would just subtract this fraction, giving me 186 minus, I'm subtracting the fraction, this 2,324 over 37. That is the value of b. Now I'd like to put this as a single fraction, right? Remember, this is 186/1. Whenever you add or subtract, you need a common denominator, right? This is subtraction here, not multiplication. So I need a common denominator, which is clearly 37, right? The least common, I'll say over here, the LCD, right? The least common multiple of the denominators is 37, right? Because 1 goes into 37, 37 goes into 37, right? That's the smallest number that both denominators go into evenly. So this fraction's okay. It has the LCD already. It's this other fraction that I need to multiply the numerator and denominator by the same number by to change the denominator into 37. The denominator is 1. I would have to multiply it by 37, and the same in the numerator. And we get this fraction. Again, I'm going to go to the calculator here. I got 37 times 186 in the numerator. So that's 6,000 882 in the numerator over, and then 37 times 1, 37 in the denominator, minus, and then this 2,324 over 37. And again, this is equal to what b is. And once they have the same denominator, right, when you add and subtract and you get the same denominator, that's the denominator of the final fraction, right? That common denominator does not change. It's the numerators you combine. So I take 6,882 and subtract 2,324, and we're getting 4,558 37ths. That's the value of b. And I'll punch this in and we'll get an approximation, right? So the value of b is 4,558 over 37, which is approximately, and I'll enter this in my calculator, 4,558 divided by 37 is about 123 point, and then I'm seeing 189, 189, 189. It's 189, 189. So 189, and then a 1 after that. So this would be to the nearest thousandth, if you will. Okay. But again, I'm going to use this, right? And just know that it's about 123.2, right? Okay. So now that I have b, I have the y coordinate of the y-intercept. I have m, the 8337. So I can fill in for b this fraction, and we get our final model. All right. So the linear model, when all is said and done, here, let me get the ruler out of here. So the model I put off to the side here is, y equals, and our slope was 83/37 times x, and then plus b, and that's this 4,558 37ths. And I'm going to use this as my model. Or you could use the approximate y equals, and what was 83/37, so it's about 2.243 times x plus, and then 4,558 over 37 is about 123.189, right? And this is an approximation, right? It's pretty, I mean, it's really close. I mean, they're to the nearest thousandth here. I'd say either one will be fine at the end because I'm done with the model, right? Just, don't round too much in too many problems is all I'm saying, right? The more and more you round throughout a problem, the less and less accurate a final result will be. All right, so I have an equation for a linear function here. Y equals slope times x plus, y coordinate of the y-intercept. Y equals mx plus b. Fantastic. All right, I know that was a lot of fractions and kind of annoying, but it's still very doable. All right, and part B. That was all part A, right? Just finding the equation of a model, equation of a line that goes through two of the points I selected, right? And I selected that 28,186 and that 65,269, right? All right, part B is just simply graph the line on the scatter diagram, all right? So I've got, here's the scatter diagram. All right, back up here for all these 10 points, that represent these 10 ordered pairs over here. And all I'm going to do is graph the line that goes through the 2 points I selected. All right, and I'll draw it in a little different color. All right. So I'm going to put my ruler here. I selected this point, right? That was the ordered pair 28,186. And I selected this point because it seemed to me that that line was, for all the pairs of points I could have picked, that line seems to be cutting through the middle the most, right? It seems to be where all the points are tending toward. All right, and then let's take this point, try to line up the centers of them, and here we go. Draw it in. That wasn't that great. And there's our linear function. And I'll even put the equation that we got. Right, this is y equals 83 37ths times x plus 4,558 over 37. All right, and can you see how, the points, these dark points on the scatter plot seem to be tending in that direction, right? The same direction as the line I've just drawn. Okay, so now I'm going to, well, that's all they asked, right? That's all they asked us to do here was graph the line on the scatter diagram. Now notice I didn't continue it this way. All right, here's our y-intercept here. Notice I didn't. Now I'm gonna actually I'm gonna label that. All right. This point has x coordinate 0. It's the y-intercept, right? X coordinate 0, and the y coordinate was that 4,558 over 37. That was about 123.189 ish, right? That was 4,558 divided by 37. All right. So here's our line. Great. Now what we're going to do with that, when you're given a scatter diagram and you're asked to, find a line, if you see a linear pattern, which I do see in these 10 points, find a line that, these points tend to follow, and then what you do with that line is make some predictions. All right, so that's what part C is about. Part C, predict the total cholesterol of a 39-year-old male, and round to the nearest whole number. So 39-year-old male, this is x, right? Our values of x was the age of these males. And predict the total cholesterol. Total cholesterol was represented by y. So this is just saying, use our equation here to find y when x is 39. All right. So that's what I'm using this equation for. All right. So we go into our equation. This y equals 83.37 x plus 4,558 y equals 83/37 times 39. I'm replacing x with 39 in the equation that I drew for this line, plus 4,558/37. All right, so all I need to do, because the denominators are already the same for these fractions, it's going to be 37. I just need to multiply these two numerators and then add 4,558. All right, so I'm going to take 83 times 39. All right, 83 multiplied by 39. That's 3,000. That's 3,237, and then add to that 4,558, and I'm getting 7,795/37, right, over 37. Now they did ask us to, round to the nearest whole number, right? So when I punch this in, I'm going to take 7,795 and divide by 37, and it's around 210.6756. It's 210.6. And that 0.6, that's higher than, that's 0.5 or higher. So I'm going to round up. The nearest whole number is 211. I remember what y did. Y was cholesterol. And what were the units on cholesterol? That was milligrams per deciliter. So this is the prediction. So I would say that I'd predict that a male that's 39 years old, based on my equation here, that the points seem to be following. I predict that a man who is 39 years old will have a cholesterol level of about 211 milligrams per deciliter. And that's the answer to that, right? That's what they're asking us to predict. And let's see if that's happening in the graph here. All right, let's see if that's happening in our graph. So we predicted, when x was 39, the y will be about 211. All right, so look at my graph. So let's see. when x is 39. So 39 years old is around here. That's the 39-year-old. Right? And what point is on the line I drew? See, that's this location around here. It's not perfect, right? I'm doing this eyeballing it. Now this isn't part of the scatter diagram, it's just a point on the graph that I drew. And you see how that point has a y coordinate between 200 and 220? And 211 is between 200 and 220. So it's looking good. It looks like our model, our graph is looking okay. All right. Now that doesn't mean, right, that a person who's 39 years old is going to have a cholesterol level of 211 milligrams per deciliter. This is just a prediction, right? That was the key to this. The word predict is in there. You're guessing, based on all these 10 points here, based on this table of data over here, right? Oops. Based on this table of data over here, based on what these 10 points are doing, we guess that a 39-year-old man would have a cholesterol level of about 211 milligrams per deciliter. Right? Okay. And then I have one final part to this scatter plot, scatter diagram, fitting a line in there and then using it to make a prediction. The final part is interpret the slope. All right. Interpret the slope as a rate of change in the context of the problem. And then also, does it make sense to interpret the y-intercept, this point here with the 0, 123.189 or the 4,558.37? Does it make sense to interpret that? All right, and I mentioned earlier, right, the slope, I'll use the approximation this time, is approximately 2.243. All right. Now remember what that means, what slope means. Remember the units on this were, a change in cholesterol, change in Y, that's milligrams per deciliter per year. Right? There was change in the cholesterol over the change in age. What does this mean? Well, remember what slope means. The slope tells you how to move on the line. When I say a slope is 2.243, that means that, remember, it's like 2.243 over 1 if you want, or you can think of it about it as the 83 over 37. But all this means is that if I increase the years by 1, the cholesterol will increase by about 2.243 milligrams per deciliter. So if I increase my age by 1 year, so that means move to the right 1 on the graph, 1 unit, I'd have to move up 2.243 to stay on the line. So that means that an increase in age of 1 year will increase cholesterol by 2.243 or approximately 2.243 milligrams per deciliter. Okay. That's what slope means. It's a rate of change. It tells you how much one variable is going to change if I change the other variable by so much. All right. For instance, a slope of 3 means if I increase x by 1, y would increase by 3. A slope of -5, if I increase x by 1, y would decrease by 5, right? Because it's negative, and so on. But a slope, that's what slope means. It tells you a rate of change. It tells you how the value of one variable increases when the value, or decreases if it's negative, when the value of the other variable increases or decreases by a certain amount. All right, now this question here. Does it make sense to interpret the y-intercept? Does the y-intercept make any sense in real life? All right, so the y-intercept is the point 0, right? This point here on the graph of my line, right? this 0, comma, and then 4,558 divided by 37, or approximately 123.189. And what this means is that a male, 0 years of age, right? That's what the first coordinate means, right? Age. Would have a cholesterol level, or I'll just say has cholesterol of 123.189, milligrams per deciliter. Now think about that. Does that make any sense to say that? A male, 0 years of age, not even born yet. So how can someone who's not even born, not even conceived, have a cholesterol level? All right, so if you really think about it in the context of this problem, this does not make sense. So I would not interpret the y-intercept. Right? It does not make sense to interpret the y-intercept. How can someone who is 0 years old, not even existing yet, have a cholesterol level? All right, so you really got to pay attention. Pay attention to what the problem is about. What is the context of the problem? What meanings do the variables have? And you'll know whether or not something makes sense, hopefully. And it takes some practice, probably takes some experience. We've seen a lot of problems like these to get the hang of that. All right, but the most important thing from this page is slope. What does slope do? Right? What does slope tell us? It's a rate of change. Tells us how much one variable will increase or decrease when I increase or decrease this other variable by a certain amount. Great. All right, so that was a lot. I know, a lot of crazy numbers, crazy fractions and decimals, but I popped stuff into my calculator, right? It made it a lot easier. But the concept's the same. If I want to find an equation of a line, pick 2 points, which I picked here and here. Find the slope, and then once you've found the slope, you can use one of those points, plug in the x-coordinate, the y-coordinate, and help you find that b, that y-coordinate of the y-intercept, and then you'll have your line. And then you can use your linear model, y equals mx plus b, to answer any question they have. Okay, great. And as I like to say at the end of these, try the best you can to learn the material on your own before you go looking for help. Obviously read the material, read the examples the author gives, maybe even try to work out the solutions to examples before you read what the author did, and maybe you can learn from mistakes that way, comparing your work to the author's. Work on plenty of exercises, plenty of practice problems, check solutions when they're made available, just to see how you're doing, keep track of your progress. Don't just give up after the first attempt at a problem, right? If after several approaches at a problem, you've tried it several different ways and you're still not figuring out how to do it, maybe then you should go back and read the material again. Maybe more slowly, more deliberately, take notes. Perhaps you should even read it a 3rd time. Because who knows, after working on some problems, you'll have a better idea as to what the author wants from you. Then you go back and read through the material again, you'll catch some things that you might not have caught the first time, or things will stick out to you that didn't the first time. But if after that, if after several read-throughs of the material and several attempts at a problem or problem set, you're still not getting it, still not clicking, then it is not a sign of weakness whatsoever to go out asking for help, go looking for help. That is what other people are there for. Ask a teacher, a tutor, a friend, someone in your class who you know knows the material well and is willing to help. Find supplemental materials online. There's loads of stuff out there. Find videos on the subject like this, and I assure you, there are plenty of videos out there on any math subject you can think of that are better than mine, and you can find them. I know you can. But just keep at it. Stay persistent. Keep practicing. Don't give up. And I think the hardest part is to try to keep a positive attitude. And it's amazing the difference that can make. Try to have fun. Try to enjoy yourself. Make a game of things. And and that might make all the difference in the learning experience. So keep practicing. Stay persistent. Stay positive. Don't give up. And I know you can get it. Thank you for watching.